Today we're going to look at how to find the rate law for a reaction given experimental data. The rate law is a way of showing us how the rate depends on the concentration of the reactants involved in the chemical reaction. So typically they might give you a chemical reaction like the one in this problem above, and they will ask you to, at some point, find the rate law or determine the orders of the reaction. Now, just because they give you a reaction and you see stoichiometry, the stoichiometry of a reaction no way implies what the orders of the different concentrations of the reactants should be. Those have to be determined with experimental data, and that's why they give us this chart below with experimental data. Now, just to review what a rate law should look like, so when I get down to part B and it asks me for the rate law should look like something like this. It should have the word rate on the left-hand side. It should be equal to some constant, which we will call the rate constant, and we denote it as a lowercase a. And then you have to put in the concentration of each reactant that's there, raised to some power. So I see that there's a Br minus as a reactant. I see that there's a BrO3 minus as a reactant. I see that there's an H plus as a reactant, and the square brackets mean concentration and molarity. And I'm not quite sure yet how their concentrations are going to affect the rate. So a lot of times when you're just writing this generally, you might give them exponents x, y, and z. These exponents are called orders of the reaction, and they might be different with respect to each particular reactant. Each reactant has its own order. Sometimes when you're writing a generic rate law, you might have something like A and B and C. Just make sure to fill in your actual formulas of your reactants that apply for the given reaction. In this case, I have 3 reactants, so I will have 3 terms in my rate law. Sometimes you'll only have 2 reactants, and then you'll only have 2 terms. So again, I'm going to have to go to experimental data to figure out these exponents or these orders of the reaction. So that's where this chart above comes in. So let's kind of examine that chart. So what I want to do is I want to, one at a time, figure out the orders or the exponents for these particular reactants. So if I want to observe the order for Br minus, just like how I would in any experiment, if I want to observe the effect of just one thing, I want to choose trials where everything else possible can be held constant. So if I look at experiments 1 and 2, the Br minus concentration is doubling. It's going up by a factor of 2. Meanwhile, the other 2 reactants are being held constant. Nothing's happening with the BrO3 minus, it's 0.005, 0.005, and nothing's happening with it different with the H plus, it's 0.1, 0.1. Now I can see how just Br minus is affecting the rate. Notice that the rate is also going up by a factor of 2. So what would the order or the exponent of Br minus have to be so that if Br doubles, the rate doubles, so that it has the same directly proportional effect? Well, that would be a first order reaction. So on inspection, anytime I see the same exact change happening with rate as is happening with the concentration of that reactant, it's a first order with respect to that particular reactant. If I wanted to, if this were like a free response question on an AP exam, or if you have a test and this is like an open-ended question, you can describe this in actual words. You can say, as in experiments 1 and 2, as Br minus doubles, so does the rate, and so this reaction must be first order with respect to Br minus. You can also show this mathematically, and mathematically you are doing exactly what we're doing on inspection. You're essentially looking at the change or the ratio from one trial to another. So what are the 2 trials I picked? I picked trials 2 and I picked trials 1. So what I am essentially doing is I am doing a ratio of the rate laws. I'm doing the rate of trial 2 over the rate in trial 1, okay, equals, and just writing what the rate law is, K from trial 2, the change in BR or BR minus in trial 2, BrO3 minus in trial 2, H plus in trial 2, and I'm doing that all over the same thing from trial 1. So I'm really just making a ratio of the rate laws. Now when I do this, what's always going to happen? Well, my rate constant is always going to drop out because the rate constant is the same as long as the temperature is the same, and it tells me in the problem the temperature is 298 Kelvin. So this really simplifies. And I can't forget to also raise all of these to the power that is their exponent, which I forgot to show. Okay, so this really simplifies. The K's drop out, and again, I'm really just doing a ratio of rate 2 over rate 1, okay, equals the concentration of Br minus in trial 2 over Br minus in trial 1, raised to some x power. The ratio of BrO3 minus in the second trial over the first trial raised to some unknown power y, and the ratio of H plus in the second trial over the first raised to some unknown z power. That's a z, not a 2. So all I'm doing is really plugging into this. My rate for the second trial is 5.00 times 10 to the negative 4. My rate in the first trial is 2.50 times 10 to the negative 4. And if I plug in with units, what are you going to notice that the units are going to do? They're going to end up canceling out because they're the same. So for now, I'm just going to omit the units because I know they've canceled out to be the same thing. Again, if you want, you can put them in, but they will end up canceling out. And then I'm just going to fill in. Okay, for my Br minus, what's my concentrations? 0.002 over 0.001 raised to the x power. Again, the units are concentration, so the units are molarity. They'll both cancel out. Okay, and I put in my BrO3 minus concentrations, my bromate ion concentrations for each trial. And I put in my H plus concentrations for each trial. Again, I just started omitting units because they're going to end up canceling out. So essentially, you can see the reason why we picked trials 1 and 2 for observing the rate law or observing the order of Br minus, because the H plus and the BrO3 minus, you're going to have a number divided by itself, which is going to give you 1. And what is 1 to any power? 1 to any power is 1. 1 to the second is 1. 1 to the third is 1. 1 to the fourth. So it's just going to be like multiplying by 1, which is not doing anything in your mathematical equation. So if I simplify this, I get 5 times 10 to the negative fourth divided by 2.5 times 10 to the negative fourth gives me 2. Okay, 0.002 divided by 0.001 gives me 2 raised to the x power. And if I want to write it in, it's times 1 to the y and 1 to the z, but those terms just cancel out. So my final equation here is 2 equals 2 to the x. What does x have to be? X has to be 1. The order of Br minus is 1. So you can show your work mathematically like this. Again, here I picked trials 2 over trials 1, and you can just show your work mathematically as I have left it here. You really don't need all that extra intro stuff that I was just doing. I was kind of just deriving why I'm showing it this way mathematically. Or you can do it on inspection and show your work as words. But just make sure you do some sort of explanation. You don't just scribble on the chart and call it a day. If you ended up having more complicated numbers, so orders don't have to be whole numbers. They don't have to be 0, 1, 2, 3, 4. They can be decimals or fractions. They can actually even be negatives if you have something like that's inhibiting the reaction. But if you had more complicated numbers, you would have to kind of do this mathematically. And then once you got down to this point, if you didn't have 2 equals 2 to the x, if you had like, I don't know, 5.3 equals 2.7 to the x, or something like that, just some different numbers, then you can solve this with logs or natural logs. You would take the log or natural log of both sides, then you can bring down your exponent, and you can solve for what that order is with logs and natural logs, which is another mathematical lesson that you can search how to do if you're not sure. But a lot of the times you will get whole numbers. It's just it doesn't have to be. So be prepared how to solve it mathematically or algebraically if not. Also, something to notice is that the order or the exponent of Br minus, it does not match your initial coefficient of Br minus in the reaction that's given, and that's totally fine and totally expected because the stoichiometry of a reaction does not predict what the orders of the reaction are going to be or how that particular concentration of that reactant would affect the rate. So let's move on and let's try doing the order of the next substance, the next reactant that's here. You can feel free to pause the video and do it out yourself. But let's do it both ways. Let's do it on inspection and let's do it mathematically because both ways are good to have in your toolbox. If you're taking the AP exam, the inspection way would be great for a multiple choice or for part of a free response to save time. And the mathematical way should be known and understood because you might have to do that for more difficult problems that could present themselves in like a free response question. So if now I want to observe BrO3 minus's effect on the rate, which trials should I choose now? I can choose trials 1 and 3. I want to choose trials where the other reactants are held constant and only BrO3 minus changes. So if I look at 1 and 3, Br minus is not doing anything. BrO3 minus, my bromate ion, is changing. It's actually changing by a factor of 1.5, which could be hard to tell on inspection. If you have trouble telling that on inspection, you can do this mathematically. My H plus is not changing at all, and my initial rate is also changing by a factor of 1.5. So if I was explaining this on inspection in my free response, I would just say in trials 1 and 3, BrO3 minus increases by a factor of 1.5 while everything else remains constant, and the rate also increases by a factor of 1.5. So this BrO3 minus must be first order. The exponent of it must be a 1, so that it has this directly proportional change. Again, you can show this via your mathematical route. I am picking trials 3 and 1, and what you'll notice is I'm always going to put the trial that has the larger numbers on top and the trial that has the smaller numbers on the bottom, so that when I'm doing this mathematically, I'm left with numbers larger than 1 rather than decimals, and I find that easier to work with. You don't have to do it this way, but I always find it easier. Okay, whatever has the higher rate, let's put that on top. Whichever has the lower rate, let's keep that trial on bottom, and then just make sure that it's consistent throughout the whole equation. Whatever you choose to be on top is on top the whole time. So I'm doing trials 3 over trials 1, so I'm making a ratio of the rates. So here's my ratio of the rates. I know the rate constants drop out, so now I just need the ratios of the first reactant, Br minus, raised to the x power, though I did solve for what x is for Br minus, so I can fill that in. So again, I can write it to the x power, but since I have my information, it might be more helpful to write it to the 1 power, since I already know the order. And let's do the ratio of the BrO3 minus, and I don't know the power of that, so here it is, raised to the y power. And we'll do the ratio of the H plus and raise that to the z power. And again, you'll notice certain terms dropping out based on the trials that you picked, and things simplifying and units canceling out as well for the ones that I put in. So this simplifies to 1.5 is the ratio of my rates, and then this is 1 to the 1 power, which cancels out, okay? And then I get 1.5 to the y power, and then 1 to the z power, which cancels out. So what does y have to be? So that 1.5 equals 1.5, y has to be 1. This has to be first order. And again, if you have more complicated numbers, you can solve by taking the logs of both sides, bringing down your exponent of y, and solving for y is. So now I have the orders of both, and again, practicing doing this both by inspection and mathematically, it's good to have both tools in your toolbox. Let's solve for H+, our last reactant. Which trials would you choose for H+? What you'll notice about H+ is you're not going to be able to pick a trial where all the other reactants are held constant. Unlike the other reactants, there are no trials where both Br- and BrO3- are held constant. And that's okay because we know how to do this mathematical route, and you just might have an extra term. So that's why I said it's important to be able to show this mathematically. So if I look at my trials above, I know I have to use the fourth trial because the only time H+ has been changed is going into the fourth trial. And then I would recommend picking trials where at least one of the other reactants is held constant because it will just make the math and the algebra a little bit easier. So I'm going to pick trials 3 and 4 for solving for H+, just because I think it'll be easier if Br- is held constant. So if I look at this, Br- is held constant, BrO3- is not, and H+ is not. But it's okay because I already know that BrO3- is first order. So even if something doesn't drop out mathematically, I'll know the exponent is raised to, and it's just one more factor in my math. So let's show out how to do this mathematically. So again, for H+, I'm going to be picking trials 4 and 3, and I'm going to put trial 4 on top and 3 on the bottom because 4 has larger numbers, so this way I am left with more so closer to whole numbers than with fractions. So on the left-hand side, I have the ratio of my rates because the word rate is on the left-hand side of the rate law, and my units are going to end up canceling out. And notice that rate is in units of molarity per second, which makes sense. It's a unit of concentration per time because it's how quick this reaction is happening. And then equals, and now I'll do the ratios of each reactant raised to the power that is their order. Here's my ratio of Br-. I know that that order is 1, so I can actually write in the order, though it doesn't matter because 1 to any power is going to end up dropping out. And I'll do the same thing with BrO3-. Here is the ratio, and I know that's also raised to the 1 power because the order of BrO3- is 1. And lastly, I'll do H+. I'm not sure what that order is, so I'll raise it to the Z. Just make sure that that's not a 2, that's a Z. And let's see how the different things drop out here. So the 3 times 10 to the negative third divided by 3.75 times 10 to the negative fourth. Oh, okay, that gives me 8. And then this gives me 1 to any power is 1, so I really won't have that term in there. Then 0.0150 divided by 0.00750, okay, that doesn't cancel out, but it does give me 2, and 2 to the 1 power is itself. Anything to the first power is itself. And then 0.2 divided by 0.1, oh, okay, that's another 2. And I'll raise that to the Z power and solve for it. So there's just this one extra factor in my algebra that's not really going to give me any trouble. 8 divided by 2 is 4, and then 2 to what power gives me 4? Oh, Z must be 2. It must be second order with respect to H+. If you're wondering what 0 order might look like on inspection, 0 order, if all the other trials are held constant and the concentration of one of the reactants changes, the rate would not change at all because anything to the 0 power is 1, so it wouldn't have any effect. And if you're wondering what second order would look like if all the other trials were held constant, if something were to increase by 2, let's say, then the rate would increase by 4. Or if the concentration were to increase by 3, the rate would increase by 9. It would be like a squared factor. So now that we have solved for all the orders, we can go back to the original rate. And in the original rate law, we just want to make sure that we substitute, instead of X, Y, and Z, we actually put in what our orders are. So the order of Br would be 1. You can write a 1 in, or you don't have to because 1 would be implied if there's no exponent. BrO3 minus is 1, and H plus is 2. If you had something to the 0 power, you could either write in a 0 or that term can drop out completely. Then once you solve for the rate law, a lot of times they'll ask you to solve for the rate constant. And now that you have the rate law, all you have to do is you can pick any trial you want. Trial 1, trial 2, trial 3, trial 4, and you can plug all of that data into your rate law and solve for K. The only thing is that you have to be aware of is when you solve for K, you need to make sure that you're also solving for units. And the units of K are going to change depending on what the overall order of the reaction is. So here the overall order is 4. There's a 1 for Br minus, a 1 for BrO3 minus, and a 2 for H plus. So the units of K are going to have to work out so that when I multiply all those concentrations raised to those orders, I end up finally getting the rate back in molarity per second. So just showing you, I'm going to rearrange the rate law to solve for K, like so. And then you can pick any trial that you want to solve for the rate law. I'm just going to pick trial 1 to make life easier. So I'm going to plug in all that data with units. Here's my rate for your first trial. It has units of molarity per second. And here are all of my concentrations plugged in. If something, just as a heads up, if something were to be 0 order and you plugged it in and you had a concentration for it, it wouldn't matter because it wouldn't affect it at all. And now you just plug and chug here with your calculator. The only thing to be aware that some people make mistakes on is in like this last term, that squared is not just, it's not just the value squared, it's also the unit squared. So it's 0.002 squared and it's molarity squared. And from here you can see what's going to end up canceling out. One of the molarities will cancel out with the one in the denominator, and I'm going to have 3 molarities left in my denominator. So if I plug this into my calculator, my final answer will be around 5,000 as my value of K, the rate constant, and my units would have an m and a seconds, have mn seconds in the denominator, but it would be m3 to the negative 3 power, m to the negative 3, s to the minus 1. Okay, and your rate constant can be very large. If it is a fast reaction, it can be very small. If it is a slow reaction, so don't let the value of or the magnitude of K throw you off. So this is a typical kinetics problem. I went through it in detail, and feel free to do more examples.